Hello and welcome to Alloy's tutorial. First thing before we start, so there is an accompanying blog post which includes some additional references, interesting links, code snippets used in this video. So what you can see at my screen right now is a draft of this blog post, but at the moment you are watching this, the blog post will be already published and the link to it will be included in a video description. So I encourage you to check it out. And the second thing is that I don't presume any prior knowledge of Alloy from you. I will guide you step by step from the very beginning, from the installation of AlloyTools, so you don't have to worry about this. And I picked examples based on how basic they are, and hopefully they will be actually easy to follow. At the same moment, it may create a false impression that Alloy is mostly suitable for toy examples, but that's not the case, and there are plenty of success stories on the web, and if you're curious about them, you can find links to them on the mentioned blog post. So I think we are ready to start. The first thing you need to do is to run AlloyTools on your computer. And to do this, you can find AlloyTools on GitHub, and you can see that it's a Java project, and therefore you can use it programmatically using its Java API from any language running on top of JVM. However, it's not the most usual way of using AlloyTools. Most of the people use it by means of graphical user interface, and that's what we'll do here too. So to get it, first go to Releases tab, and you can see that the recent version of AlloyTools is 5.10, and that's the version we'll use in this tutorial. You can see that there is a jar file listed here. We need to download it on our machine. And since it's a Java program, it should run on any operating system without problems. Before running a jar file, just for the record, I will check my Java version. So I'm using Java version 8, but I think any Java version newer than 6 should be enough. So right now I just need to run a jar file. I just download it, and not so beautiful UI appears. It's not beautiful, but this is what it is. And it has a menu called file, and you can see all the usual things here. For now, I will just open one of my recent files. You can find it on the blog post too. So in your case, you probably need to create a new file and to copy paste the content. It's probably the most basic or the most minimal example you can write in Alloy. It's a very basic specification. But before diving into what it means, let's focus on how to actually run it. So there is this button execute, and if I click it, Alloy will try to come up with examples of the model specified within this specification. And it found an instance. You can examine the instance clicking on the link, and a new window pops out, and in this window we are able to browse through all the examples generated by Alloy. And the first example is a bit odd, and I think the message is also misleading. So there is nothing wrong with anything here. It just generated an empty example. So an example having no elements at all, and it's a valid example according to the specification. It's not an interesting one, but you can stumble upon this from time to time, so don't be surprised. And now to go to the next example, we need to click on the next button. And now we can see an example of a single atom called A. Let's go next. And now we have two atoms, A0 and A1. We can go even further and we have A0, A1 and A2. So as you can imagine, those names are coming from the name of the signature. I called it A, and that's why Alloy come up with those names A0, A1 and A2. Those names do not carry any meaning. They are generated just so you are able to distinguish between different atoms. And what are atoms, by the way? So in Alloy's terminology, atoms are instances of signatures. So if you think of signatures as of definitions of sets, then you can think of atoms as of elements of sets. So now let's try to go to the next example, but there are no more examples. And the reason for that is how we specified our show command. Let's focus on the run command for a moment. Run is one of two commands available in Alloy. The other one is check, which is used for looking for counterexamples. So going back to run, as you can see, you need to pass the name of a predicate as a first parameter. In our case, it's show, and in our case, it's an empty predicate. But in general, you can put any number of logical expressions to the body of the predicate. The second parameter, in our case 3, specifies the size of solution space we want to explore. So let's try to change it to 2 and let's see what happens. As you can see, in this case, the biggest solution, the biggest example, is comprised of 2 atoms, which makes sense. So all in all, you can read this command as try to look for examples satisfying predicate show in which the number of atoms of each signature is at most 2. And at most is an important addition, let's say here. There is also an option to look for exactly 2. It actually needs, in this case, we need to specify also the entity we are interested in. So let's try to run it now, and we should get only one example. So that's the only example. It is also worth knowing that in a run command, you can replace the name of the predicate with its body. So in our simple case, I can run it like this, and I should get the same result. Now I will introduce another signature, mostly to present you how you can control the solution space of each signature separately, but also to give you a short preview to relations. So I'm introducing a new signature called B, and it will has one relation called parent of type, let's say, A. So this line specifies that each atom of signature B is in a relation called parent with exactly one atom of signature A. So let's try to run it. And as you can see, Alloy requires us to also pass the number of B. So let's try it with 1B. And that's the first example. It makes sense. So there are 2 A's and 0 B's, but it makes sense because, as you remember, 1B means at most 1B, so 0 is included. And the second example looks as this. There is 1B actually, and additionally it also shows you how the relationships are visualized. And I think that's all. So it's good to know that you can configure run with such granularity. There is one very important thing to note here. So by specifying those numbers in run command, you don't restrict your model. That's because the commands are not actually part of specification. So specification are signatures, predicates, and facts, assertions. They specify your model. And commands, they just describes how you want to interact with AlloyTools. So by saying exactly to A, you are just saying that in this modeling session, let's say, you are interested in models or in examples having exactly to A's, but it doesn't states that on as a constraint or invariant. You can have multiple commands in a single file, so I will add some more. I haven't mentioned that yet, but you can omit the number of cases at all in the run command, and in this case, for free is assumed. So those two lines are equivalent. Let's try to run it. And you can see that only one of those commands were run. That's because how execute button works. It only executes the first command in a file. So if you want to run a couple of them at once, you need to use execute all. And as you can see, 3 commands were executed. And we can take a look at those samples. So that's all when it comes to run command. And now let's proceed to predicates. But before moving on, I will comment out signature B just to keep the model extremely simple. And let's stick to the default run and let's write the first non-empty predicate. I will call it at least one, and in this predicate we'll constrain our model so we have at least one A atom. So there is operator hash and it returns number of elements in a set, and we constrain it to be greater than 0. And now I also need to refer to this predicate in a run, so like this. And now we don't have an empty example anymore, which is good. Okay, let's write another predicate, this time not a single one, and it will state that the size of A cannot be 1. Let's use it here and let's execute that. And as you can see, an empty one is back. Let's go to the next one. So as you can see, the example with just 1A is not present anymore, but an empty one is back. So that's because we don't refer to at least one anywhere. We only refer to not a single one. We need to add another predicate, this time more than 1. And it will be a conjunction of at least one and not a single one. And I'm using a Boolean operator AND that you probably know from other programming languages. Now I need to refer to more than one, and let's execute it. So we are presented with 2 examples, one with 2 and one with 3 A's. So that's what we would expect. We've learned a couple of things about predicates. First is that predicates are not run automatically. They need to be referred from run command. Another thing is that we can invoke predicates from another predicates, like here. And also we can compose our predicates using logical operators. One more fact about predicates is that they may contain multiple lines, or rather multiple logical expressions. So I can rewrite this more than one predicate in the following fashion, and it will be equivalent, because if a predicate has more than one line, they are assumed to be combined with AND operator. So let's try it out. Yeah, it works the same. Another fundamental building block of specifications in Alloy are facts. Superficially, they are very similar to predicates. However, there are some crucial differences. Actually, you can turn a predicate into fact just by changing a keyword. And let's try to run it. We cannot refer to facts. So let's comment it out for a moment. And let maybe also run it with an empty predicate. And let's see. So we have an example with 1a. So it proves that this predicate was not applied. And we also have 2a's and 3a's. But we didn't have an empty example, which means that that fact was applied. So let's try to turn this predicate to fact 2, and let's see. Yeah, so we only have 2 and 3a's, which means that both of facts were applied. More than this, you can also invoke predicates from facts. So let's turn those facts to predicate again. And yeah, we'll use it, we'll make it a fact, and it should be equivalent. Yeah, as you can see, it's the same. At this point, you may say, well, we achieved the same result with both predicates and facts, so what's the difference? The crucial thing about facts is that they are always applied, and therefore they cannot be invoked because there is no point in invoking them. That property makes them a perfect match for modeling global invariance, properties of your system that are always true. How about predicates? What are they good for? So first of all, since they can be referred from run command, they can allow you to look at your system from different perspectives. So for example, in a given modeling session, you may be only interested in a subset of all possible examples. And in this case, you can express it using predicate in scope of a one run command without over-constraining your model itself. Secondly, and more importantly, predicates can serve as a unit of reusability. And if that sounds a bit abstract to you, let's consider such example. Let's consider that we also, I haven't mentioned that by the way, but facts don't have to be named because they are never invoked. So I will introduce another fact, this time without any name. And let's say that in fact I want to say at least one or not a single one. That example, this particular example doesn't make sense, but in principle you may want to invoke your predicate in a different place, but compose it somehow differently. So here we compose them using AND operator, and here using OR. And if you imagine predicate at least one being some very lengthy condition with 8 operators involved and so on, then you can see the benefit of being able to abstract it only once and then reuse it in a few places. Let's move on to the last topic of this video, which are assertions. Everything we've done so far was revolving around the idea of exploring your model by inspecting examples generated by Alloy. It's a very valid use case, but it's only one of two main use cases of Alloy. The other one is looking for counterexamples. Okay, let's write the first assertion. In this assertion, we will verify that number of a's is always greater than 2. And let's try to run it. Let's comment this out. Similar to predicates, I need to refer to this by its name. As you can see, Alloy is complaining that it cannot find a predicate called greater than 2, which makes sense because there is only assertion which is called greater than 2. So the thing is that we use run for running predicates, but we use different command called check for running assertions. So let's look for counterexamples, and counterexample was found. The counterexample contains 2 a's, something which is completely valid with our specification, as the specification only constrained the number of a's to be more than 1, but it doesn't say anything more. And at the same moment, we also asserted that the number of a's should be always greater than 2. And that's why it is considered a counterexample. Let's take a look if there are more counterexamples, but there are no more, and that's expected. And to fix that counterexample, I will do something which is completely against the spirit of Alloy, but it will demonstrate the mechanics of how counterexamples are found. So what I will do, I will simply state it as fact that number of a's is always bigger than 2. And that should be enough to fix the counterexample. So there is no counterexample found anymore. Why did I say that it was against the spirit of Alloy? So this particular case actually was very close to cheating, because we just copy-pasted the logical expression from assertion. But in general, I would say that your assertions should be written using different terms than you use for facts or predicates. Let's say you are designing a system built on top of 3 basic operations. Then you may end up with encoding all the knowledge you have about those operations and about their implementation at the level of facts. But then you also want to say something about a system as a whole, and that would be a good candidate to be put at the level of assertions. So those would be things like, given any sequence of basic operations, system cannot enter illegal state. So as you can see, since those observations are more high level, they should probably also be expressed using more high level terms on Alloy level. To conclude, we've learned that there are two main modes of using Alloy. The first one is to explore the domain by examining all generated examples, and the second mode is verifying that your model is correct by looking for counterexamples. That's all I've prepared for today. Thank you for watching.